ठीक है।
टॉप देखते खाओ, टॉप देखते खाओ।
Abhishek, are you audible?
Yeah. Am I audible right now?
Yes, please go ahead.
So let us all welcome Basudeb Dasgupta da. He is a alumnus of RKM 98 batch, and after that, right now he is in TIFR, Tata Institute of Fundamental Research, working as in the theoretical physics department. He is working as a associate professor right now. And after passing from RKM after class 10, he has done his BSc Physics Honors from Jadavpur University. And after that, he did his MSc in Physics and PhD from TIFR itself, Bombay. And he is a very academic person, and he has done a lot of research fellowships, and he has a lot of certifications also, memberships, and he has been the president of certain committees also, not only in India but foreign also. So he is a CCAPP fellow from Ohio State University as well, and Center for Cosmology, Theoretical Physics, and Astroparticle Physics, CCAPP, I think. So while you are discussing, you can just let us know what all these terms and conditions mean.
Yeah, those things are not very important, but anyway.
Yeah, meanwhile, people would like to know about all those things also. Yeah. And the major highlights are like recently in 2022, he got Shanti Swarup Bhatnagar Prize, which is the prestigious award in the science field of science. And in 2022, also he was featured in 75 under 50, the scientist shaping today's India. So that's a very prestigious for us also. 2020, he has also featured in the Asian Scientist Top 100, I think. Top 100 list, he was there. 2020 also, Swan Jayanti Fellowship, he completed his fellowship there also. And like this, there are many associations with the academic and various prestigious institutions also. He was also Ramanujam Fellow, I think, in 2015. And currently, he also serves as the editorial board on the editorial board of the European Physical Journal. So, without wasting much time, I would like Basudeb to start with his presentation, and I hope it's a very interesting session and very enriching session for all of us. So, Basudeb, over to you. Kindly continue.
Thank you, Abhishek. Am I audible? Can everyone hear me?
Yes.
Excellent. Okay, so first of all, thank you for that very detailed and very nice introduction. I'll tell, hopefully, but that was part of my plan of actually telling my brothers from TIFR a little bit about what this academic life is about, because many people don't understand it, don't know much about it. And I think if nothing else, I think I can tell that. And that should be of some value. I mean, because sometimes, it may happen that you may have to advise some young person in your family or in your friend circle कि अच्छा PhD क्यों करोगे, करके क्या होगा, science पढ़ के क्या हो सकता है. So at least at that very practical level, I wish to achieve that one thing, that people should know a little bit more about the academic career ही कह लेते हैं इसको. Although I feel that, it's very rich and very beautiful life, of studying science. The other thing that I want to achieve is maybe try to tell you a little bit about the kind of science that I do. Okay, what exactly am I doing? So, ये थोड़ा difficult है. ये is not very easy to communicate exactly what I do, because it requires quite a bit of prior preparation, but I will try. So with your permission, I would like to start now. Okay. All right.
Sure,
so first of all, thank you for inviting me. I should thank Ritesh da, Abhishek, I think Rishida also was in contact. Many of you, please forgive me if I, have forgotten anyone important. I should also thank, everyone else involved in Vidyapit, Maharaj. In the end, we have all come together because of our past associations. So by first of all thanking every one of you, let me start. Okay, so first I will tell you a little bit about the work that I do, and then at the end I will come back to my own personal journey, my career, and feel free to interrupt me at any point and ask questions. Okay, I will hope that either Abhishek or someone else who's co-host will help me with taking the questions and doing the logistics. But let me start. Okay, so the type of science that I do, first of all, it's in the field of physics. And within the field of physics also, I work on theoretical physics. So I don't have a lab, I don't do experiments. I basically work with mathematics and computers, but I study physical systems. In particular, I study stars and galaxies and these kind of things, and how the microscopic laws of nature, so atomic physics, subatomic physics, particle physics, how those microscopic physical laws are important in these astrophysical and cosmological circumstances. That is the broad brush picture of my research. So within that broad brush picture, there are many other things that one can do, but just to give you a sense of where I am and what I do, this is our campus. What you see on your screen, this picture, these buildings in the front, that is TIFR. The entry is actually from the other side. So where all these other tall buildings that you see, these are buildings in the Cuff Parade area of South Bombay. And there's a road that goes in front of our buildings, and in those other buildings in the background are actually about 1 kilometer away. But this road brings us down, south from much more frequented areas of Bombay, like VT and so others, Cuff Parade and these areas. So if you come down this road, here is where we work. I work on the 3rd floor of this building. And as you can see, we are right next to the sea. There is this, beautiful campus with a beautiful lawn and everything. And I'm not alone. There are about 150, 200 scientists who work in this institute in different areas: physics, chemistry, biology, mathematics, computer science. And within the Department of Theoretical Physics, where there are around 20, 25 professors, I am working with 4 of my other colleagues in this area that I told you about on cosmology and astroparticle physics. Okay, so that's roughly what I do. And I'll tell you more about the logistics and the human aspect of this, but let me move on to the scientific part. I want to tell you 2 things today. The 2 kind of things that I do. I do other things, but these are 2 important things. One of them is something that, I was given the prize for, the first one. And the second is something that I just did very recently. So this is very, very recent. This was published literally, I think, this year with one of my students. And I want to kind of give you a sense of what I get excited about and what I like. So the first thing I will tell you about is how something very interesting called collective oscillation happens inside exploding stars. So there are stars that explode at the end of their lives. These are called supernova. And then inside these stars, there are particles called neutrinos, and they have some interesting behavior, and I'll tell you a little bit about that. So that's the first thing that I want to tell you. And the second thing that I want to tell you is how certain stars can collapse at the end of their lives, even if, even though they were not supposed to, if dark matter is of a particular kind. And this is something that we, discovered and predicted only very recently. So these are 2 things that I want to tell you. Okay, so first thing, so neutrinos from a supernova. So here is a cartoon. So this gray, pink, and yellow, these circles, they're basically a cartoon for the different shells of this very large star. And there are these subatomic particles called neutrinos. So these neutrinos are basically like electrons, very small particles, but they don't have electric charge. And their mass is 1 million times less than that of the electron. So they're very light, they have no charge, and they're very weak interaction. So they can pass through material very easily. And as a result, these particles are produced in large numbers inside the cores of these stars, and then they leak out of the star. As they leak out, they are responsible for two very important things. One thing that they are important for is nucleosynthesis. Nucleosynthesis means that creation of nuclei. So all these elements that we see in the periodic table, most of these elements are actually made inside stars. The calcium in our bones, the iron in our blood, the oxygen in our lungs, all these chemical elements were actually made inside stars. And if neutrinos were not there, and if neutrinos did not do their thing, we would have more or less of these elements. And the world and the universe as we know it would be not there and be very different. So that's one of the things that neutrinos do in the star, that they create these elements. They're responsible for creating these elements. I'll tell you more about it. They're also responsible for stellar heating. So these neutrinos are what make the star explode, because as these neutrinos are going out, they dump their energy in the star, and then the star explodes. And if neutrinos did not do that, basically supernova explosions would not happen. Okay, but nevertheless, these neutrinos eventually, most of them escape the star, and along the way, as they're leaving the star, they do something interesting, which is called neutrino oscillation, and I'll tell you more about that. Okay, and then eventually you detect these neutrinos on Earth using various experiments. Hopefully, I'll be able to tell you about that also. So, but the big picture is this, that there's a star, let's say in our galaxy. This star is of a special kind. This star is a bit massive star, about 8 to 10 times more massive than our sun. And then it makes neutrinos, and in 10 seconds, the star explodes and emits these neutrinos, which do lots of things, and then we detect these neutrinos. Okay. Now, the funny thing is that although this is a very rare event, this happens about once in 30 years in our galaxy. Statistically, we have been very unlucky, and we have not seen any such explosions for basically our whole lifetime. But nevertheless, we believe that there will be one in our galaxy within some time. And there are lots of efforts to detect these neutrinos. So, all these are names. You don't have to read everything, but it gives you a sense that there are literally a few thousand people interested in what one can do with these neutrinos. And then what can you do with these neutrinos? As these neutrinos escape the star, in different time periods, lots of very interesting information about the star and about neutrinos and about lots of other physical effects can be studied and measured using these neutrinos. So to give a very broad rough picture, I would say that this is a laboratory. Usually people think of doing science in a laboratory inside some building, but universe or nature itself provides a laboratory, and these exploding stars which emit neutrinos which are detected on Earth, this provides something like a cosmic laboratory, and that's what we are after. Okay. Now, I told you that I'll tell you about neutrino oscillations. So this is a very interesting thing. Usually, when we make something like a particle or apple, orange, whatever, that thing remains what it was. So suppose I have an apple and I throw it to my friend. The apple remains an apple along its path. Now, quantum mechanics tells you that this is not always the case. So neutrinos are one of those examples of quantum mechanics where you can have a particular kind of neutrino. Let's call it an electron neutrino, because it is produced in the radioactive decays associated with an electron being emitted or a positron being emitted. So this neutrino, when it is sent from point A to point B, it does not remain an electron neutrino all along its path. Okay. It changes to a different neutrino and back, and again back to electron neutrino and back. So it keeps doing this oscillation. And this is because of quantum mechanics. Now, there is some interesting mathematics that, that describes it. Basically, this equation that you see here, this is a form of the Schrodinger equation that describes quantum mechanics. And what you see here as a cartoon of what happens is, as a function of distance, which is on the horizontal axis, on the vertical, I'm plotting the probability, the chance that what I started as an electron neutrino stays an electron neutrino. And the two different curves corresponds to two different neutrinos, let's say with different energies. They're emitted with different kinetic energy, So, and it turns out that whether they oscillate quickly or slowly, that depends on their kinetic energy. So this is what neutrino oscillations roughly is. I can tell more if there are questions. Now, what happens inside the star, inside the supernova, is that this type of oscillation is completely changed. You don't just get this oscillation. So two things happen. First of all, as you saw, here, normally neutrino oscillations, the two different neutrinos with different energies are oscillating in a slightly different way. Their oscillation wavelength, the speed with which they oscillate is also different. And you can see that they're oscillating a lot, that their amplitude for oscillation, the depth of these oscillations, that is also quite large. This is what normally happens. But we predict, actually, that inside the star, first of all, this amplitude of oscillation will become very small. And the different energies, different neutrinos with different energies will all oscillate together, as if they're bound to each other, which is why you don't see a different blue and red curve here. And not only that, the most interesting thing is that there are these very sharp glitches, that suddenly all the neutrinos, from one flavor, they go to another one. This is called an instability. So these are predictions. So these are not just my predictions. There are lots of people. So this work started in the 1990s. And early 90s, 1992 was the first, paper on this field by this gentleman called Pantaleoni. And then I started doing my PhD in 2003 and started working on this problem in 2005. So which was almost already, let's say, 10 years, 15 years after this field started. But I was very lucky that between 2005 and 2015, there was a lot of activity in this field, and there was a huge amount of progress that was made. And we also got, the chance to make some contribution. So this is basically the main scientific result that I was involved in. And the two key ideas to remember, if you want to remember anything about these technical aspects, is that inside stars, neutrinos, change their flavor from electron neutrino to some other neutrino more quickly and in synchrony with other neutrinos. So the collective and instability. So more quickly is this notion of instability, that something happens suddenly. And the fact that it happens together is this notion of collective. And there's more details. I can answer questions later if needed. My particular contribution was actually proving a theorem. So it's a mathematics theorem. I proved a theorem that this whole business of collective instability happens only under certain conditions. Only if certain condition is satisfied by the physical, system, by the neutrinos in this, then these collective oscillations happen. And again, these are just pretty pictures. I don't want to go into the details of it, but you can imagine now the kind of work that I must have done, that there is this star which is emitting neutrinos, it can be detected, and so on and so forth. There is a prediction for these collective instabilities, as they say. And what I did was I predicted when this happens, or what are the conditions under which this happens. This is a little bit similar to how we prove in school that when will the roots of a quadratic equation be real versus imaginary. Actually, the thing that enters the proof is quite similar. Just in school, we learn, right, that there's this discriminant in the quadratic equation, b square minus 4ac. And if it is positive, then the roots are real. If that is not positive, but it's negative, then the roots can become imaginary or complex. And that's the kind of work that was done here. Okay, so the details are not important. And then what it does is it actually affects what you will measure on Earth. So one example is this. So imagine that you're tossing a coin and you ask, will I get a head or will I get a tail? And the answer is, often people say, well, it's 50-50, isn't it? But you should be a bit careful. I mean, why can't we predict exactly whether it will be a head or a tail? we can, we can take very sharp video of exactly this flipping process, and we know exactly the physics laws that govern the motion of this coin. Why can't we just predict whether it will be a head or tail? And the answer is this, that as a function of how much time in air the coin spends, if you look at the left box, and as a function of how much spin I gave it at the beginning, the following can happen. Either you can just go up and come down without spinning even once. This is a very bad toss. So you basically get exactly the same phase that you started with. Or it can take one turn and come back. Or it can take two turns and then come back, and so on. And we know exactly when that will happen. So these stripes are actually telling you that there is 0, 1, 2, 3, 4, 5, and so on number of flips. And if you realize, what happens is that we don't know exactly the initial velocity with which, the speed with which we toss, and the initial spin with which we toss. So we are uncertain, and we basically, only know in a certain range, which is given by this box. And in this box, you can get head or tail equal number of times because there are all these stripes. And this is the reason why a coin has 50-50 probability of being head or tail once you toss, because you have not measured the initial speed and the initial spin. Okay. Similarly, because these neutrinos are oscillating inside this star, but you want to predict what exactly happens to it at the end, you have to use ideas like this of probability and statistics to then predict what happens to these neutrinos, and which is what we did. Okay. And then once you do that, you can predict that all these elements, this is periodic table of chemical elements, which you must have seen, all these elements, in particular the ones that are in green, blue, and yellow, orange, all these elements are actually created in these massive stars. So basically all the elements except hydrogen, helium, lithium, beryllium, and boron, the first 5, all chemical elements are actually made in these stars. And because these chemical elements are made using radioactive beta decays, which involve neutrinos, all this neutrino oscillation physics is important. Okay. So that's the first, sort of things that I wanted to tell you about. The second sort of thing that I wanted to tell you about is something to do with this gravitational wave detector, LIGO. Okay, so now we know that there is this gravitational wave experiment going on, and it is detecting black holes. We realized that this instrument can be used to study dark matter also. Okay, so in particular, what we found is that nowadays there are detections of black holes which are of very low mass. So one of them was, for example, seen to have a mass of 2.6 times the mass of the sun. There was another one which was seen to have a, so this is what basically the first page of academic papers. Our work is often, written up in academic papers. There's a website called Archive. You put it on that archive, then eventually it is sent to a journal where other people check it, and then eventually it gets published in the journal. But papers look roughly like this. This is a title, there's a date on which it is submitted, there's an abstract which tells you roughly what has been done in this work. And this is just to give you a sense of what goes on in the business. And one of the interesting things that appeared a couple of years ago, just 2020, if you see, is that they discovered a black hole which has, fairly low masses, less than 5 times the mass of the sun, could be as low as 1.12 times the mass of the sun. Turns out that such low mass black holes are actually not allowed. So there's a minimum mass for a black hole, and it is approximately 2.7 times the mass of the sun. Now, it is possible that nothing crazy is going on, that, these black holes that we are seeing in LIGO are just completely regular, and it's just measurement uncertainty which is making their mass appear to be small. Actually, the mass is a little bit big, that there's just some measurement problem. It is possible. Or that, as scientists are prone to do, they invent lots of new ideas. And, these are a whole bunch of ideas. There are ideas all, stretching back all the way from 1960s, Russian scientist Zeldovich, and then Stephen Hawking, and so many others, so all of these ideas about what can give rise to these very light black holes. And we came up with one idea, and the idea is as follows. A very simple idea, that we know that we live in a cloud of so-called dark matter in our galaxy, and a neutron star can capture this dark matter, and we then show that if that happens sufficiently efficiently, then this neutron star will just collapse into a black hole. And then the black hole will have a mass which is the same mass as the neutron star, plus a little bit from the dark matter, but that little bit is very little. Okay, so this was our main idea. And this is what in pictures it looks like. So this red blob is like our whole galaxy, and the red dots here are the dark matter particles, so to say, and the blue circles are neutron stars. So imagine that there are two neutron stars near to each other which are going around each other. So it's called a binary. Then this dark matter, the red dots, they go and gravitationally they get attracted to the neutron star. Once they enter the neutron star, they undergo a few collisions and they settle in their core. Once you have attracted a sufficient amount of this dark matter, it can just collapse into a black hole at the center of these neutron stars. And these black dots are, showing this tiny black hole. And then this tiny black hole eats up the rest of the neutron star. And you get these two very light neutron star mass black holes that go around each other. Okay, so this is a prediction. We made this prediction. And now what we are waiting for is, LIGO is going to start seeing hundreds and thousands of these black holes over the next decade. And if it sees such an event, if it sees these very light black holes in large numbers, it will give some way of testing whether this dark matter is there or not. And if it does not see these black holes, it will actually tell us that, black hole does not have certain kinds of properties and so on. So with that, I think I will stop the scientific part of the discussion. If there's interest and questions, I'm very happy to take them. But let me just finish by telling you about how this work was done and, what is all involved. So what happens is that right now I am a professor at TIFR. So I have PhD students who are working under me. At some point of time, I was a PhD student and I was working under my advisor, also at TIFR. And these are the students who have worked with me, the first two. So this person, Sulagna, she is my current student. I've had several other students who are not shown here, but the people who have worked on these two projects I'm showing. These two people are students, and the next two are postdocs. Postdocs are those who have done a PhD and then they come and still work with you before they become professors. And then these are two of my other students. This is another postdoc who worked with me. And we are not alone. So there are, TIFR, we do these, scientific work. Although this is completely theoretical and based on mathematics, we need computers to do our work. And we have a lot of staff that gives us help with computing. And we are also largely funded by taxpayer money. So Tata Institute of Fundamental Research, which is where I work, is under the Department of Atomic Energy. And all of our funding, my salary, my student salary, all of our work, all computers, everything comes from the Department of Atomic Energy. It's taxpayer money. We also get external funding, for example, from DST, which is also again taxpayer money, but also external scientific agencies. So for a large portion of my career, I was actually funded by the Max Planck Institute, where I also worked as a postdoc for 1 year or so in Munich. So I was funded by them. So that's how this work was done. That you do a PhD, you do a postdoc, even a couple of postdocs, in my case 3. Then you eventually become a professor in a research institute or a university, IIT somewhere. And then you have your students and you write papers. You study things, you write papers. These papers get published in scientific journals after being peer reviewed. And there are others who do experiments, they run labs, and they sometimes test your ideas. And if you're lucky, you discover something interesting. But even if, you're not that lucky that you've discovered something that gets tested and verified by experiment, and the journey is a lot of fun because every day you are solving a little puzzle. So those of you, who know young people who are interested in solving puzzles, this is a very interesting field to work on. Okay, so that's the end of my presentation. I'm sorry I went maybe a couple of minutes over. I was asked half an hour, but I think I'm already at 32 minutes. But this is the main message I wanted to give you, that I work on
टायर भी
particle
चेंज कर
physics.
देगा, स्टेपनी वाला इसमें डाल दीजिएगा,
I think yes.
इसमें
Yeah, please continue.
Yeah. So, so just to kind of summarize what I've told you, I work in the area of theoretical physics, specializing in the area of astroparticle physics, which is a mixture of astrophysics and particle physics. Some of the work that I've done has to do with neutrinos, stars, dark matter, black holes, this kind of stuff. And I've also tried to give you a little glimpse of what exactly is the journey, like in terms of career that one takes. You do a BSc, you do then a PhD, you do a couple of postdocs, then you get a job as a professor, assistant professor typically, and then eventually, you grow within one of these universities or IITs or TIFR or ICERs are there. So all of these places you can do research. And this is just one example. There are people working in all sorts of different areas. So most of them are actually experimentalists. But I think I have more or less told you what I wanted to. So at this point, I would like to stop. And if there are questions, I'm happy to take them.
Mhm. Thank you so much, Basudeb. Actually, you made a very technical topic, non-technical for a non-technical audience. I think that was the key takeaway for me, because when I first looked at the slides, I thought that this is going to go over my head. But I think it was very well presented, keeping in mind the background of the audience. So thank you so much for that. So we have, I think, one question. Vinayda is asking that in which year the last explosion took place actually. So you said that it did not happen during our life. So maybe.
Yeah. It's a very good question. Actually, no one knows. There isn't a very clear answer to that question. We know that one of these supernovas, so this is a particular kind of supernova called type 2 core collapse supernova. We know that one happened in 1987 on 23rd February. Okay, so I was not that young, and I was 4 or 5 years old. So in principle, I should have memory of that because it was actually visible by naked eye. But it happened not in our galaxy, but it happened just outside our galaxy in a place called Large Magellanic Cloud. That's the closest supernova, to us in, forever. In our galaxy, I think for at least 100 years, there is no supernova. Part of the reason is that there could have been a supernova, but if it happens behind the center of the galaxy, then there is too much dust and you can't see it. So that's the reason why I said that no one really knows. Yeah.
Yeah, so anyone else has any questions or comments or some observations, then please unmute yourself and then you can start speaking. So Ritesh has actually pointed that we have two physicists and chemists in the audience, so Professor Sen Gupta and Sayan Roy.
I apologize to them for maybe toning the whole thing down, too much. I apologize for the oversimplification.
No, Basudeb, can you hear me?
Yes, I can.
Very nice seeing you, and also very nice to see a fellow physicist. I am on the other extreme of the spectrum, both in length scales as well as context. But again, I think it's wonderful to see you also spend some time in Germany. Actually, I did my PhD in Max Planck Institute at the time in Göttingen. And but great to see that you are doing some excellent and contemporary physics related research. So when did you move back to India, if I may ask?
Yeah, so I moved back to India in 2014, so end of 2014 actually. So I've been here for 9 years at TIFR now.
Yeah. So do you keep coming to Europe once in a while?
Just for work every now and then, yes. About a couple of times a year. So
okay.
Yeah. So I travel
please,
less and less these days, but
do keep us posted.
where are you exactly,
Luxembourg? Sorry?
Where are you in Europe?
So currently I'm in Luxembourg. So if you've been in Germany, you might know where it is. It's a small country
I know where Basudeb is.
flanked by France, Belgium, and Germany. And so also I'm not here alone. Ritezda is also here in Luxembourg. It's
I
a
see.
funny coincidence. It's, I think, the highest probability of finding two
Two Ramakrishna Mission Vidyapit people in
Mission
Luxembourg.
people
Somebody
in
should
terms
work that
of
out.
square kilometers. Yeah. So,
Yes. That's
but
really
yeah, we are very well connected to all major European hubs. So if you are in Europe, please make sure. I'm in the Department of Physics here. And also, I think the topic you are working on, it resonates very well with many of my colleagues and also particularly many of our students here at the university. So
sure. Next time I'm in the neighborhood, I'll certainly,
certainly, yeah, you are warmly welcome.
Thank you.
Dada, I'm having very silly question.
Yes, Bikash.
I just wanted to know your view on this. What is the size of universe and what lies at the end of universe? Do you ever could attempt to explore those things?
Okay, yeah. So, so the question I think was, what is the size of universe and do we know these things and how do we know these things? Is that the question?
Yeah, Dada. Also, what lies at the end of the universe?
Okay, so this is a very interesting question. I don't want to, go too deep into this subject because it will take us very long. But let's start with a simple picture that imagine that there's an ant that lives on a rubber band. And so as far as the ant is concerned, there's nothing more than that rubber band. Okay, so there's an ant that lives on a rubber band or the surface of a balloon, if you will. The balloon is hanging in vacuum, there's nothing else. And there's an ant on the surface of this balloon or a rubber band or whatever. Where does this balloon end from the perspective of the ant? Or how big is the balloon? Okay, so we who are living in 3 dimensions can look at the rubber band or the balloon, which are 1-dimensional or 2-dimensional objects. We as 3-dimensional beings can look at it and we see that there is something beyond it. But people who live on the surface of that universe, of that balloon or the rubber band, have no idea what's beyond it. And neither do we. Okay, so we live in a 3 spatial dimensional universe, and then time in relativity is thought of as 1 more dimension. But beyond our universe, this question does not make sense within our perspective. Now, size, you can give a size. For example, for the balloon, there's a notion of a size. There's a radius of this balloon, there's a circumference of this balloon. So that number is known. That number is roughly 14 billion light years. Okay, so that's the size of the observable universe. But yeah, this is a very interesting question. It'll require a full 1-hour talk.
Thank you, Dada.
Basudeb, yeah. Please, Gautama, go ahead, please.
Basudeb, I am Gautam Sengupta from the 1969 batch of Vidyapit. I guess most of us, I mean, you talked about watering down the topic, but I think for most of us, even this version, much of this version is impenetrable. And yeah, I mean, that's not an observation on your ability to explain. It's just how things are. Now, I have a question about how thinking in this fascinating part of theoretical physics goes on. So I'll start with a very brief example. So for example, we have these embodied notions, like let's say length, breadth, height. So these 3 dimensions, we have very intuitive embodied, very intuitive understanding of. Similarly, we have a kind of very intuitive notion of ordinality. So let's say first, second, third, fourth. But language, grammar, allows you to combine these 2 notions. So you can talk about the You know dimension, you know first, second, third. So you can talk about first dimension, second dimension, third dimension. But language, by its very nature, allows you to create expressions like 10th dimension or nth dimension, of which the ants that we are, we have no intuitive idea, right?
Yes.
So it is only symbolic manipulation that sort of allows you to get there. I'm sure a lot of theoretical physics that you do is also like that. So essentially, you combine symbols by rules of grammar, in this case, the grammar of mathematics, that allows you to combine these things and come up with constructs of which you can possibly have no intuitive embodied notion. How does thinking work under these circumstances? How do you get these aha moments? Or how, for example, you have an inkling that there's something going on there. Let me try to capture it. Give us a glimpse into these thought processes.
So first of all, Gautamda, I think you explained it far better than I would have.
No way.
This was amazing. This was excellent. So yes, so the question is that, first of all, there's a very important observation that Gautamda made, which is we often talk about things that are beyond our immediate experience. And we make most of our progress based on rules of mathematics. But is there anything more? Do we get some of our aha moments in a somewhat less, let's say, dry manner? And the answer is yes. In fact, that's a very important question. I'm really grateful that you brought this up and you explained it so beautifully. So most of the time, we are dependent on symbolic manipulations based on the rules of grammar, as you said, the grammar of maths in this case. But there are two ways in which we go past it. One way we go past it is using analogies. So although we may be talking about the 10th dimension, so to say, but if we focus our attention on a particular aspect of this problem in 10 dimensions, for example, maybe we are interested in something that's happening at the edge of this 10th dimension, then all of the other stuff does not matter. So we may live in 3 dimensions, but as long as we are confining ourselves to the surface of the earth, a 2-dimensional description is sufficient, right? Similarly, by focusing your attention to portions of a given problem, you can make the problem simpler and more amenable to attack by your intuition. The second way in which you can make progress is through analogies with other things that you know. And this is used very, very frequently. So once we understand one thing, and this is one of the beautiful things about physics, that there are a handful of things that you really have to know and understand. After that, other things are simply just the same thing in a different garb. So for example, in our undergraduate course, we learn about thermodynamics of gases, pressure, volume, temperature, and so on. Turns out this thermodynamics is usable in understanding black holes also. Now, black hole is not a gas, but there are properties of black holes that obeys the laws of thermodynamics. And therefore, we can learn a lot more about black holes. We can do everything that we've done for ideal gases in our undergraduate, but now for black holes, and learn many new things. And this is one, very important way, using dualities and analogies, like very mathematically precise analogies. These are called dualities or mathematical reformulations of a problem. So yeah, so that's the way we make progress. If I am allowed to add, I may add that, so because you asked theoretical physics, I said these two, but actually a huge amount of progress is made by our, our counterparts who do lab experiments or observations. So if you're an experimental physicist, you can, of course, measure things, and you can, tinker with a system and learn a lot more about it. And in that case, you give information, to the community, in particular theoretical physicists, who can use this additional information to learn more about the system. Maybe I've done a calculation without any intuition first, but then I get a bit more data. I can then check whether my theoretical model is consistent with this new data or not. And that's the third way in which I can make progress. Did I answer your question somewhat?
Yeah, Basudeb, it's very beautifully answered. But if I may just ask a follow-up question, a brief one. So coming to experimental physics, let us say, again, just assume I'm a novice here, I know nothing. So I'll just cook up some idea to communicate what I have to say. Let's say we are talking about the 10th dimension, right? And of course, I have no intuition. I could possibly have no intuition about the 10th dimension. However, I can come up with a theorem that sort of suggests that by assuming 10th dimension, I posit the existence, the occurrence of such and such phenomena.
Mm-hmm.
Some equation, something that it's a consequence of that.
Exactly.
Now, in an experimental setup, all you will be able to verify is the existence of that phenomena.
That is true.
Which means all you are saying is the existence of this phenomena can be explained, so far as we know now, only if we assume the existence of this 10th dimension.
Only is a strong word, but
only is a strong word. Exactly. There could be others also, because our knowledge at this time is limited. However, that still is far, far away from any intuitive grasp of the 10th dimension.
That is true.
It's simply a matter of consistency within a theory.
That is true. That is certainly true. So yes, we understand this, that, there is a very beautiful quote which more or less encapsulates this point of view, which is that all models are wrong. Models also, in this case, also includes theories. So all models are wrong. Some are useful. Right? So the idea is precisely that you will never be sure that you have a theory that is completely correct. So in science, we are not in the business of providing certainties and statements about that this is proved. Mathematics gives you proofs. If that's why I use the word proof very selectively when you do math. You have assumptions, you have axioms, you can prove things. Science, physics in particular, is not in the business of proving anything, but we are in the business of strongly favoring or strongly disfavoring explanations. We are also in the business of saying that something cannot happen. There's enough data, there's enough evidence to then tell us that certain things just don't happen. So there are constraints on reality that are imposed by physical laws. That's something that science provides. We also provide reasonable, plausible explanations for what's going on around us. We provide useful models to predict what may happen in the future, or what can happen under given circumstances. But you are completely right that in any given situation, we can never be sure that the model or the theory that I used in order to make a prediction that happened to be true is the correct explanation, let alone be the only correct explanation. Is that roughly what you wanted?
Yes. But picking up on your mention of models, the flip side of this argument could be that, well, models are all there is. That is, all understanding essentially is creation of models.
That is true.
So both W.V. Quine and the great physicist, I forget names. the one who passed away recently. A movie was made on his life. You mentioned him also in one of your
Hawking?
yes, yes. Both of them, for example, at one point say that existence is, I mean, if I understand Hawking to some extent correctly, existence is basically a postulate in a model. So you are creating mental models, you are creating models, trying to make sense of the universe. And that is why you postulate objects.
Yeah.
So
But you see,
models
it's
could be
not
all
that
various ones.
different from what one does. Let's say if one works in a soap manufacturing company. Okay, so imagine that I work for whatever, Godrej, and I am, let's say, an operations manager. I hope that there are some in the audience who can correct me if I'm saying something wrong. But then I'm tasked with this idea that, okay, we are making all these soaps in this factory, and here are all our distributors, come up with a, way to make this very efficient. And you come up with some method that, okay, the trucks will do this, and then, the people will be guarding my warehouses in such and such way, and this will be the rough demand at this place and that place, and you make certain assumptions, and based on that you provide some solution. Now, we take in our daily lives, this is precisely what we do, and we take it as the reasonable thing to do. But this is always under the assumption that, first of all, your prior experience is correct, or like is applicable in this case. So for example, it may just so happen that you've made all these plans, and then there is COVID, and the amount and the demand for soap just shoots through the roof, and all your calculations are wrong, and you've made a big loss. If you had just kept all your soaps in Bombay, where you produced them, or you would have sold out everything within a week. But now that all your soaps are stuck in these warehouses or inside trucks traveling along the road, you are going to incur a loss. So your model broke down, and there are consequences. But this is also true in our very day-to-day life. Every time you take a step forward, you get off your bed, you stand up, and you try to take a step forward, you are intuitively and almost involuntarily assuming that gravity continues to work and friction continues to work in the way that your life experience over the last n number of years has taught you. But this is how so you have a model of how the world works. A child touches something hot, gets burned the first time, knows not to do it again. All of these things are just models being made in our head.
Exactly.
And that's what we live with. So as scientists, we do basically the same thing, but we have a bit more control on the models that we are making, usually, at least as theoretical physicists, because our systems are relatively simpler. We're not talking about human psychology or consciousness or something, where we don't know exactly how to manipulate the system. We're usually talking about systems that are better understood, more under control, and therefore our models are much less frequently wrong.
Basudeb, absolutely fascinating. You are not only erudite, you are extremely clear in your expressions. I am personally grateful to you for this talk. Thank you so
Thank you very much for that lovely questions.
We have one more question in the comment box. It's from Rajiv Da. So he asks that how do you see ideas like quantum mechanics being distorted and often misinterpreted in popular science fictions?
Okay. That's a very nice question. I'm happy somebody asked this. Okay, so there are two parts to that question. I think it is really fascinating if people explore scientific ideas in their day-to-day lives, including in art and theater and movies and fiction. I think that's a great thing. And I think a certain amount of license should also be taken in interpreting these ideas. I think it is a little silly to say that, okay, if you're writing science fiction, the science that you put in science fiction must be totally obeying every law of physics that's known to man. I mean, you can do it, that's your choice, but as a scientist I would not demand that, because our knowledge of science is also evolving. So I would say a creative person should take liberties, but then, society and the audience will judge whether those liberties were taken for good reasons. Did they actually achieve something? So, for example, there are movies where they suddenly will say that, okay, let us make quantum mechanics applicable not just to tiny things where quantum mechanics has large effects, but let's imagine a world like this Ant-Man and Wasp or whatever, that kind of a movie, where quantum mechanics starts affecting big things, macroscopic things. It's a great idea. One should explore these ideas. And in fact, doing so, even as a scientist, forget for entertainment, as a scientist is a very useful thing, because that's exactly how you learn more. You explore the consequences. So that's the first part. What is not good, and that's really the part I think maybe the question was hinting at, was when incorrect things, or I would say motivated speculation, is peddled as hard science. That, I think, is something that we as a society should strongly discourage. It's totally fine to come up with a story. What is not good is if you then pretend that this is hard evidence-based science, when that's not the case. Okay, so we should distinguish between stories and science, because science, what we call as science, that's the reason why I tried to show you, some of the more technical things. Like, for example, why am I showing you the first page of a paper? I mean, I could have just written it down. Why did I show you this is how a paper looks? Because I want to give you a sense that when people do, science is a method. Part of that method is peer review. Part of that method is being evidence-based. Part of that method is being able to make predictions. It's not sufficient to explain something. You should then be able to say that, okay, under these assumptions, I predict the following must happen. If not, I will throw away my theory. You have to have that confidence and that humility. So those ways of learning or gaining knowledge which do not obey the scientific method, that should not be called science. And that should not be then sold as science. I think that's something to be very careful of in our daily lives, in how we trust or not trust some information. But also as a society, by now, many of us are in positions of responsibility, where we have to make decisions which affect other people. At least you are making decisions which affect your family. And there it's, I think, super important to distinguish between science and, in the worst cases, pseudoscience. Right? So I think that's very important.
I have Vasudeva, one question. So you started your presentation by saying that your research is largely funded by taxpayers' money. So
Yeah.
that brings in the picture that there is some public support from the government to science in India. So my question is, in the broader perspective, do you think that the current public ecosystem that we have is supportive for research in the country, or is there something more that can be done? Firstly that, and vis-a-vis, because you have stayed both in US and now in India, so what all things that you saw in the US that can that the say a Ministry of Science or uh, some public changes that can be brought to encourage more of research, more people taking on theoretical research in the.
Okay, so Satyam, you asked two questions. First question was that is there sufficient public support for science in India? And second question was, in comparison to, let's say, countries like Germany and USA, where I spent some time, is there something that we should be doing, maybe in particular in the case of theoretical research, which we are not yet doing? So that's the kind of question. So let me try to answer these two questions. I personally think that for a country of our size and our socio-economic development, the support for science is there. It's reasonable. It could be a bit more. Right now, we are spending, I think, 1.3% of GDP on science and technology. It depends exactly on how you count it. It could go up a bit. I think it would be helpful. But I would not say that there is insufficient public support for science. So at least traditionally, until from independence until now, I think there has, for a country with our difficulties, we started as a very poor country. It's actually very surprising how there was so much support for science in a country like ours. See, Bangladesh and Pakistan and Nepal don't have the kind of scientific ecosystem that we have. And that's something to be very proud of, I think, that we in our country, we have achieved in 50, 70 years a kind of scientific maturity that only about 20, maybe 30 countries in the world have. And most of those countries are rich countries that benefited immensely from imperialism. And whereas we lost. There are hardly any countries with the same kind of complex history as ours, with the same kind of scientific workforce. So that's something, I think, that's the perspective I take. That being said, I think in the last 5-10 years, all over the world, there has been, I feel, a change in mentality in the public sphere. I'm not talking about government. I'm talking about in society. There is, I think, a shift towards more, I would say, more short-term and more, I would say, I think the support, so there has been a shift towards short-term gains, and the support for basic science in particular requires having a very long, horizon. So there have been studies that are done in the US, for example, that tell you that if you take a sufficiently long horizon, let's say 20 years, 30 years, investment in basic science is actually one of the highest return on investment activities. No other investment gives as much return as investment in basic science, not applied science, basic science. You invent electricity, next 100 years, you can laser. But you cannot plan for that. If you're trying to invent electricity and you're trying to invent laser with the aim of making money, usually you will not discover something very important. But it takes time. So that's the answer to the first part of your question, which is that, is there sufficient support? Yes. Things have changed slightly all over the world, partly because of changing mood of the people. But I would not panic. Things are okay. We should keep in mind what is good for us. The second question is that, can we learn something from the US and from Germany in particular? I say for sure. I mean, their scientific communities are more mature. In one of the few things that we can certainly learn from them is better administration of science. So, for example, in India, large numbers of students don't get their salaries on time. So a lot of people who work, they don't get their funding on time. This has been a problem for the last, any number of years, but it's become really severe in the last 10 years. And that's very bad, because that discourages young people who are already underprivileged, from joining this field of activity. If you're very rich, then you don't care whether you get your salary or not. You can do it for fun. But then you are underutilizing, the demography of your country. There are people from all sorts of places in the country, who can contribute, but you are forcing them not to contribute and go into some other area because this is not a reasonably well-paying job. So that's one thing that we should certainly learn from them. And then as a society, I think we should attempt to be more rational. It's not that we are not rational. We are rational. There are elements of irrationality and superstition in our country, as in any other country. But we should see what is positive in other countries like US and Germany and other places. We should learn. We should take what is good. I think this is also what Swami Vivekananda says after he comes back, right? That, we have a lot of good value, but we have a lot of problems also. And what is good in the West, we should learn. I think I agree. I mean, when we were told these things in school, it seemed, I don't know, at that time I did not think too much of it. But now in retrospect, you can just simply, you can only marvel at how truly insightful and enlightened a person must have been to have recognized such basic and important facts about our society. In a very short time. So that's really.
So any other questions, if there are, or otherwise we can call it a day. I don't think there are any more questions. So thank you so much, Basudeb. It was a privilege for all of us to listen to you. Thank you for your time, and I think we had a wonderful discussion after the presentation also, and the presentation was also well timed, well presented, and I think well presented to a non-scientific audience. So that I would say, thank you so much, and. I think Basudeb has shared his email ID. So in case anybody would like to get in touch after it, so you can always get in touch with him. So with it, I think we will call it a day. So thank you so much.
Thank you,
for having me.
Basudeb.
It was
Thank
a
you.
real pleasure.
Thank